Hi, everyone, and thank you for joining us for our first IQC Fireside Chat of 2021. I'm John Donahue, the Scientific Outreach Manager at the Institute for Quantum Computing. The IQC is a multidisciplinary research institute at the University of Waterloo, studying the potential and development of quantum information science. We have researchers working on the cutting edge of physics, chemistry, mathematics, computer science, and engineering. And during these Fireside Chats, we hope to learn a lot more about the people who are discovering how the quantum world works. Before we get started, just a couple quick housekeeping notes. During the Fireside Chat, we'll be discussing life, careers, research, and science. First, we'll be going through some prepared questions. Afterwards, we'll be opening it up to questions from you. To the right, you should see a chat box. Enter any questions there, and we'll get through as many as we can by the end. We'll also have a survey link posted in the chat by the end. Please take a moment to fill that out and help us shape the next Fireside Chat and other virtual events from IQC. For our next Fireside Chat in February, we'll be chatting with IQC alumni Thomas McConkey, now a microwave systems engineer at IBM Quantum. We have excited chats planned after that, including with quantum chemists and quantum communications experts, so be sure to follow us for more announcements. Also, keep an eye out for Quantum Shorts. We're happy again to be a scientific partner of the Quantum Shorts Film Festival this year, hosted by the Center for Quantum Technologies at the National University of Singapore. On Saturday, February 13th, we'll be hosting a live screening of the 10 final short films, moderated by myself and Dr. Mark Terry from Wilfrid Laurier University's Department of English and Film Studies. We're also partnering with the Apollo Cinema, so be sure to grab some popcorn and join us then. You can keep an eye on our YouTube channel. We'll be posting that very shortly. But today, we're joined by Professor Shohini Ghosh. Shohini is a professor in physics and computer science at Wilfrid Laurier University and an affiliate member of the Institute for Quantum Computing. She is a past president of the Canadian Association of Physicists and the NSERC Chair for Women in Science and Engineering, as well as the founding director of the Laurier Center for Women in Science. She is a TED Senior Fellow and author of the recent release Clues to the Cosmos: Amazing Stories Behind the Greatest Discoveries in Physics. Her research interests are in theoretical quantum information science, spanning connections between chaos theory and quantum physics, entanglement theory and quantum communications, as well as studying equity, diversity, and inclusion in science. Shohini, thank you for joining us today around this lovely fire.
Hi, John. Nice to be here. Hi, everyone. Enjoying this virtual fire.
Yeah. I hope I always we got to start working on little mail-out kits, like just a little tiny space heater that we can gather around just to make it a little bit nicer. Yeah. That'd be good. Yeah, it's a nice snowy day.
Virtual wood to throw on the fire.
Yeah. Ooh, I smell a startup in there somewhere.
Gotta be something.
Something is out there. So first off, how have you been doing the last few months? How has the lockdown been treating you?
Well, probably as good and as bad as everybody else, as in, up and down, trying to cope with everything that's happened, kind of happy that 2020 is done and we're seeing a light at the end of the tunnel, focusing on my online teaching, trying to become, an expert in, all of the Zoom settings that are out there. Boy, I work in quantum security and I just can't even figure out Zoom security.
It's a whole different world. It's a whole different world out there. So, because as an expert in quantum security, this is a question we like to start off with, kind of ask everyone and kind of see how people's answer differ. We always talk to quantum experts, but if you ask 100 quantum people this question, you'll get 100 different answers. So kind of in a quick form, what does the word quantum mean for you?
Okay, easy questions, right?
starting with the gimme.
Yeah. Quantum. So I'll do a kind of like a word association. So how about that? So quantum word association to me is possibility. And the reason I say that, I'll explain a little bit, is at the scientific level, it's because, of course, the theory itself is a probabilistic theory. And probability to me is possibilities of different potential outcomes. And, the technical sort of description of it, if I had to give a quantum talk, then I would probably define quantum as, perhaps the Schrödinger equation that describes everything. But to me, quantum is broader. It's a way to, embrace this idea of probability and possibility as a powerful thing, rather than, something that we perhaps historically have focused more on precision and determinism. Mm-hmm. Now we're learning that, combining precision and, probabilistic kinds of approaches can be really empowering, both for science and perhaps even for society. So,
yeah. I like that. Embrace the uncertainty of it all. Just
exactly.
Yeah, a little of the most optimistic view of quantum nihilism I've ever heard, I guess.
We have to sort of see the bright side of everything, especially these days, right? We're really learning about uncertainty in every way. So.
So interestingly, you talk about like kind of embracing the uncertainty, thinking about the hope, and then when you look at a lot of your publications, a lot of your research base is in something called quantum chaos, which, I mean, if anything is talking about embracing that uncertainty, it's going to be, thinking about the chaos. But I also get the feeling when people hear the word quantum chaos, their eyes kind of glaze over a little bit and they just don't know what you're going to talk about then. So can you tell us a little bit about what quantum chaos means and what it means to study quantum chaos?
So now that you mention it, you're right. It's a terrible word choice, isn't it? Quantum and then chaos. Wow.
Hey, it gets people interested, that's for sure.
I don't know. Maybe everybody runs the other way. But it's a good question to ask, what is quantum chaos? Because actually the current answer is nobody knows, which at a scientific level is actually interesting, because of course, one of the reasons we do research is to try to answer the unknown kinds of questions, right? Explore what we know now, but what else is there, right? What we don't know. So quantum chaos actually fits into that category. Why? Well, because quantum theory is well established, certainly in the sense that, it's existed for now over a century. We understand mathematically the framework, and we have never seen a violation of quantum theory yet. So that's a pretty strong theory. And on the other hand, chaos theory is also pretty well established. It's way older, actually, than even quantum theory, because it's really something that came out of, almost accidentally emerged from observations of things like the weather, right? So, people like Lorentz and also researchers before him were studying these very interesting equations which seem to have this instability in it. And I think the most common understanding, or the common way we describe this, is the butterfly effect. So the butterfly flaps its wings here in Canada, and eventually there's a storm in Australia, for example. So small changes can lead to big effects. That's broadly what we mean by chaos, meaning quickly things become unpredictable again. So it's a form of, again, we go back to, unpredictability and uncertainty, but not in the same way that as quantum theory describes it. So given that, it wasn't really clear how the chaos theory version of unpredictability and this sensitivity to initial kinds of conditions, how does it connect to quantum theory described by something like the Schrödinger equation, which describes probabilities as well, therefore uncertainty. So here's two different types of uncertainty, but we don't know how they connect. And that's actually quite a deep fundamental question about the foundations of quantum physics and how it relates to large-scale macroscopic systems such as the weather or population dynamics and things like this. So, it's not a very clear-cut one single parameter kind of model that we can come up with. And so when I say nobody knows, it's because we haven't really identified what are the specific parameters that are the universal ways to model chaos and how it affects the quantum world. And therefore that field of study is quantum chaos. And I guess I like it because there seems to be a lot that we don't know, which means, I can spend my whole research career working on it.
Yeah, I find a nice, usually it's not a bad piece of research advice for young researchers, is find something weirdly complicated that'll, you'll spend the next 40 years.
Yeah, keeps me busy. And it's kind of fun now because on one hand, it feels like, okay, it seems a little bit out there and, not necessarily useful from an applied point of view. But now, because of quantum computing, it's really important to try to understand how multiple quantum particles interact with each other. And as we add more and more of those particles and build a large-scale multi-qubit quantum computer, we might have to really understand how those interactions might lead to chaos and chaotic behavior, and whether that'll hurt the computing power or help it in some way. So it's now got applied sorts of reasons to study it too. And it's a deep foundational question. Even Einstein pointed it out as a really important question. So, it must be important. So,
yeah. So I guess when I think about chaos theory, I think about that as being, systems starting with even like the three-body problem, where things get just mathematically complicated very quickly. And when I think about quantum computing, it gets its advantage from, or one way to think about the quantum advantage is that it comes from it's incredibly difficult to simulate even a relatively small number of qubits on a classical computer because it gets too complicated. Obviously, there's a big gap between the amount of information you can encode in a small quantum computing chip versus the amount of information encoded in global weather patterns. I'm wondering, like, at what size does this lens on quantum information become relevant? I'm imagining it's not super relevant for studying 1 qubit problems, but maybe I'm even wrong there.
No, that's a good question, and you're right that often we talk about the weather as an obvious example of something like chaos theory, which sounds very macroscopic as an effect. And it perhaps is not surprising that there's complicated behavior and dynamics in something as complicated as weather. Of course, that's not necessarily surprising, but it's way more surprising that you're right. Chaos or this kind of random behavior dynamics can show up, as you said, if you take two pendulums and couple them together. There's all kinds of YouTube videos on this. If anybody wants to check them out, they're so cool. They're like kind of mesmerizing to watch these pendula do these bizarre shapes, right? So you can see chaos at the simplest of levels, which means even at any system that has more than just one dimension of motion, if you like, a degree of freedom. Is fair game for chaos. So in fact, it is the approach, for example, in my own research is to try to look at the simplest version of the problem, right? Keeps the math as simple as possible as well. So how can we understand even, let's say, 2 quantum bits interacting? Is there a way to observe any kind of chaotic behavior there? And what can that tell us about the macro system eventually? So yeah, I think simple is nice because there's enough complexity even in simple systems, even on the quantum computing side, as you correctly pointed out.
Yeah. If you want to start understanding something, don't dive into a 50 qubit system right away.
Yeah, not a good idea.
Probably going to end in tears.
Start small, baby steps.
Yeah, 1 step at a time.
1 qubit at a time, as we say.
Exactly. Plus, it stretches out that research career a little bit. Gives
right? Every year at a qubit, maybe.
If only.
There you go. Now we've found the one strategy to build a quantum computer. 1 qubit a year.
Yeah, I gotta get a little tracker, a little something that you press a button every year, get a little nice little trumpet or something. Sounds nice, encouraging.
Like that.
All right. So outside of quantum chaos, you've kind of established yourself as a bit of a spokesperson for quantum. You've appeared on things like PBS, Nova. You've been at numerous TED and TEDx events, including as a senior TED fellow now. So I'm wondering, what do you find rewarding about kind of communicating science more broadly, like outside of with your grad students and even with undergrad students?
I mean, who doesn't love talking about the stuff that they love to do with, the whole world? So for me, I think it's rewarding, certainly on a personal level, to be able to share the kind of work we are doing and to share, in general, the excitement of science. I feel like it's the one thing that connects us all, right? So there's an approach there to not just, talk about the science, but use the science as a way to connect us all and remember that in the end, it's about us all collectively. Because science, the good thing is, of course, science doesn't care about who we are individually. And I often say that the laws of physics work the same. And you can test this out. Everybody falls due to gravity. So there's that. It's a very strong experimental demonstration that physics doesn't care about who specifically we are individually. So to me, that's an important reason to be able to share, the science with everyone, because science is for everyone and science needs everyone to engage with it, because it's about collective progress in the end. Yeah.
Do you have a memory of the first time you had to speak publicly about science?
I don't know if I remember the very first time, but I could tell you about a memorable time, which was one of the first times, because this was about 10 years ago. I was at an event in India where I was born and raised in India before moving to Canada, but I went back to India for this event. It was this award ceremony, and so they were interviewing me and asking me to describe my work in quantum. But and this was for, of course, a public audience. And in India, when we say public audience, it's on a different scale in terms of numbers. So they were broadcasting this on TV.
Okay.
So I don't even know how many millions who were watching. That's the standard viewership in India.
But a nice small broadcast, yeah.
Yeah, really. So I was already sweating about that. But what the reason I remember it is that this was an interview in Bengali, which is my native language. I'm from West Bengal in India, but I don't do physics in Bengali, right? So I'm not quite sure how to say, entanglement and, quantum wave function and such in Bengali. That was interesting to have to figure out ways to visually describe a lot of that in Bengali. So that wasn't memorable for me, but it was also fun.
Yeah, no, that's sometimes the best way. Like, whenever you get those kind of experiences early, I find it sometimes the best way to get good at communicating those kinds of things is get thrown into the fire right away, and then everything after something like having to make up words on the fly in front of millions of people on TV, anything like this is nothing.
Exactly.
When you're thinking about how you communicate science publicly, like how do you approach preparing like a presentation for that kind of public audience, different than you would, say, a scientific conference presentation? Not just in terms of content, obviously, but in terms of how you speak, what the style of the presentation is.
Actually, that's evolved for me over time, and currently, actually, I would say I don't differentiate between the two anymore, and I'll explain why. Because I guess I've having had to speak at TED and other events where they're very, very, very good about providing support and a lot of training around communication. I think the key point that I learned from all of that is that in the end, whether it's a scientific presentation to a technical audience or talking science with a broader community or whoever is the audience, of course, we need to know our audience, but the common tool or approach that really works and is successful is storytelling. So for me, that is sort of the guiding principle. So when I do, for example, a scientific talk to a technical audience, when I start writing the talk or creating it, what I first ask is, what's the story? Whether it's or if I'm writing the paper, right? What is it that I want the reader to know most? And lead with that, and then explain why that is the most important story. So, what, for example, what did you do? Why is it important? And why should the reader care? And whether the audience member care? And whether the audience member is, also in my field or, not, that will determine what level I answer the questions at, right? The questions actually are the same, because the questions guide the building the story. So that's how I have started thinking about science communication in general. Storytelling is everything. What I feel.
It's key. It's key. And yeah, I do find that's one thing I do always recommend, like even for people who don't really care that much about science communication, getting some ideas about how to communicate that science is going to help you with your academic communication as well.
Absolutely.
So outside of like these live presentations, you recently published Clues to the Cosmos, amazing stories behind the greatest discoveries in physics. What drove you to publish that, and what drove you to kind of write that? And I guess first off, tell us a little bit about the book.
Yeah, so actually I will tell you about the process, because then it'll be clear what the book is about. So there's a few reasons that, eventually led me to writing this. And the first actually is a reason I didn't even realize it was a reason for writing the book until much later. So it's really interesting, because when I first started at Laurier, I was teaching this introductory astronomy course for non-physics majors. Right? It's one of these large courses for anyone who wanted to take astronomy, and there was no math involved, or minimum math, and just a course for those who really needed an elective or who had an interest, something like that. And in teaching that course, which was just generally a general science course, but in teaching that course, of course, we covered the breadth of all of the big ideas, relativity, and a little bit of quantum and Newton's laws and optics and everything. So astronomy is a great course, because you essentially get a scan of almost all of the big ideas, right? Dark matter, dark energy, everything that excites me. Black holes, of course, time travel, everything. So in teaching it, over the years, I taught it for many years, and I sort of ended up figuring out ways that I wanted to tell the stories behind all of those kinds of big ideas. And I learned from what works with the students. And remember, this is like having students who have a very broad background or no background in science. So a lot of that had to do with drawing them in somehow. So the storytelling was shaped by that in terms of who this would be for. And so after going through that, I realized I collected enough of those kinds of ways of telling these stories that I could put it together, and that became Clues of the Cosmos. It's really just about looking at each of these big ideas like relativity. Everybody's heard about relativity, but I don't think everybody has an idea of exactly what the theory is and why we needed it. Did Einstein wake up one morning and say, here's relativity? Of course not. So
no, everyone thinks that, so that's fair. Like, that's the picture everyone default has in their head.
This is about deconstructing that a little bit and discussing how these stories are built. Many people contribute, and it's a process of discovery, right? You have all the clues, so it's like a detective story. You gather the evidence, make measurements, you build your model, then you test it, and so on and so forth. And so this tells a story from that approach, and who are these people who were involved in the story. So that's what Clues to the Cosmos really is all about.
So I'm wondering a bit, because your background's in the quantum physics of it all. Like, how did it what was like the research process there to figure out that history and make sure you had it right?
Oh, that's a really important piece, of course. So I spent a lot of time doing research. It took, many years. The book was developed over many years. And lots of fact checking, and my publisher, of course, provided fact checking support as well. And so I sort of made sure that the hard thing about writing about historical events and is not the science part, because of course it is what it is, right? You can state the theory and explain it. But talking about the human aspect of it, the people and who they were and how they thought, you don't want to put yourself in there inadvertently, right? So I found that to be a really, major challenge, I'd say. And so it took research about this to me was a little bit different from research into science itself. So researching historical people is about making sure you have multiple different resources and, being able to see that person from many different angles. And then figure out what you can say that's reliable. So I don't know if that works, but that's the process.
Yeah. So I'll actually put an image of the book out there as a bit of a plug, but for our viewers joining us from Canada, it might be a little hard to find. You mentioned, we were talking a bit offline about that before. Can you mention the publication process and where people might be able to find it?
Yeah. So the book is actually published. It was launched in India. So the publisher I'm talking about is JACO, who's based in India. It's India's major English language publisher. And to me, that was deliberate because when I talk about the book and I say it's published in India, a lot of people say, why in India? And I say, why not in India? Right? And being, from India originally, it was important for me to have the book, widely read in India and have that as being just as valid as launching it in wherever else, right? North America, which is typically where, people start with this stuff. So that's why it's actually currently available in India. I think you can order it on Amazon.ca, but it's probably going to ship from India. And eventually it will be available, through a local publisher in Canada and North America more generally. But that's where that is. And also in India, actually, I was looking through all of the authors of, books in science in India. And so I looked into physics books in particular, popular physics books. And, of course, all the big names are big there too, like Stephen Hawking and, Neil deGrasse Tyson and so on. There are a couple of Indian authors also on that list, but there's no woman author in that list who's actually, well known in India. So, I think that that's an important thing to me to have that as an example. And I hope that's inspirational for the next generation.
That's a perfect segue to the next topic then. So you're currently acting as the founding director of the Laurier Institute for Women in Science. And in addition to things like being the past president of the Canadian Association of Physicists, your work with, for example, Eden Hennessy on those traveling photo research exhibits. I wanted to talk a bit about EDI initiatives right here, because I find that when a lot of people think of like STEM EDI initiatives, they think, okay, we're an organization, we're going to throw a girls' event here and there. Obviously, there's a lot more than that to making a impactful equity, diversity, and inclusion initiative. So based on your work that you've done through there, how do you think we should be thinking about impactful EDI initiatives?
So you're right. This here and there approach is really the issue, I think, here. We don't address it in a more systematic way. So our approach through the center is to develop a framework which is very much informed by what I am familiar with as a scientist. So as a scientist, if I want to study a problem, I don't just say, okay, here's my best guess of what will work. That's not how I would start, because it would probably be doomed to failure. So similarly, if you want to, address, for example, or increase the number of women who choose to have a career in physics, probably shouldn't start by saying, well, I think this will work. Let's just have a camp for, as you said, girls, and that'll fix it. I mean, without actually thinking, wait, let me take a step back. If I have a physics problem that I want to address, I don't start with that first, just my own opinion of what works. I go and look at the research. I look at what's known, what's done, what actually works, what doesn't, what approaches have been tried, and what's left to be done. Especially with data collection, right? You want to make sure you test things. So our framework is that scientific framework. Let's apply that, but now to this question, the general problem of, diversity and inclusion. And what I mean by that is the framework is about, data collection. Let's make sure that we assess and understand through demographics as well as experiences and environmental kinds of assessments, to try to understand what is the status of the field, right? How are different individuals experiencing being a physicist or a scientist in general? Who are we in the field, for example? So surveys and demographics. So we need the data. Let's start there. And then once we know where we stand, we can identify, okay, here's what's missing, here's the problem, here's the experience that needs to change, and so on and so forth. Here's the access that is missing. And then from that, we build wise practices. And some of these are known. It's not like we have to start from scratch. There's been decades of research in this area. We as perhaps physicists are not necessarily experts in it, but there are experts out there. So just like, when we need help with our health, we go to a doctor. So, we can go to the experts when we need help with this. So we do that a lot in our center, where we get the experts in to help us build those best practices. Then we try to implement them and communicate about them, and then also continue to do the assessment and build some kind of a process of accountability if something it doesn't work. Just like in a lab, right? If your experiment fails, you can't just walk away from it and pretend it works.
Right.
If our
You can
EDI,
try, but
our EDI initiatives are not working, we shouldn't ignore it and just say, well, we did it. Oh, well.
Mhm.
So we have to continue to want to improve as well. So
Mhm.
that's really, I think, an approach that works better. And when we've applied that model, what you see is things like what you're mentioning, the mentoring and the girls' camps and those kinds of approaches, which are very common, are, part of this general approach of trying to help the girls or fix the women, is what we call it, to adapt to the system, rather than looking at the bigger system itself and saying, is the access there? Are the resources available in an equitable way? Are opportunities there? What is the, are there implicit biases?
Mhm.
What are the hiring practices? What are the, funding practices? So if you look at those kinds of questions that are about the system itself, you find that there's lots of those issues that need to be fixed, which will not be fixed if we only continue to mentor the women.
Mhm.
We have to actually fix the system to allow the women to succeed.
Right.
So that's part of what we are focusing on a lot.
Okay. So, I mean, it sounds like the first step of all this isn't to just throw a dart. Like, if I'm to paraphrase what you said, the first step is not to just throw a dart at the wall. The first step is to collect that data.
Yeah, absolutely. And actually, there's also data that already exists. So certainly you should try to assess your own context to some level. But generally speaking, we have a lot of, good data that tells us broadly where we stand. So you don't have to start only from your own data. There's some things that are already known that you can also count on and use.
Is there anything out there that you see kind of commonly being done that's maybe wrong in a counterintuitive way? People who are well-meaning, but if there's something that you wish you could say, no, it would be more impactful if you did it just this a little bit different.
Yeah, actually, one thing that comes to mind, unfortunately, is that a lot of organizations and institutions, including the ones we have also in Waterloo, offer lots of EDI training these days. And unfortunately, the studies show that training is not effective across the board because of many reasons. One of them being that people who either the training is done if somebody is resistant to it, it's really not going to be helpful. It's just a tick the box kind of approach. Secondly, even those who are open to the training, once they go through the training, there's this reaction, unfortunately, that we are all human, so we think of it almost like, oh, now I'm cured, right?
Right.
In fact, the effort put into future such EDI activities is lower because you feel like, oh, you're trained. Obviously, you don't have any more biases because you already addressed that. So that's a little bit of a sort of wrong approach. It doesn't mean training itself is bad because training is about raising awareness, education. But I think how we frame it and how we approach it, there are better practices such as building workshops, ongoing kinds of actions around it, and making sure that there's always every such training, which should not even be called training, probably workshops and those kinds of conversations really is the way to look at it, and then have ongoing actions that are clearly identified and a way to come back to it to make sure that it really is working rather than the one shot and you're done.
Right. It's not a vaccine. It's a
it's a terrible
never-ending effort.
For our times, maybe we should not be saying bad things about vaccines. Yeah, let's avoid.
Fair enough. So you're obviously continuing to act with this and continuing to be active in this area. I'm wondering, speaking of vaccines, what specific challenges you think EDI efforts are going to face during COVID and in this kind of post-COVID world that we're entering? Maybe, hopefully.
Yeah, I think that studies are already showing that the impact of COVID on things like scientific research, is definitely having a negative impact on certain communities. As in, there's now a bigger gap, for example, in research output, among those who are caregivers, for example, at home. versus everybody else, because that's obviously going to be one of those direct results. And and that of course would primarily impact women who are typically the primary caregivers. So it's almost like, it's perhaps not an intentional effect, but that's just how a lot of these things become gendered, right? Mm-hmm. So there's that happening. There's some positive impacts because, for example, some of these online kinds of conversations are perhaps more accessible to some people who would not necessarily have that opportunity mm-hmm. to engage with this work or with these kinds of groups and interactions. So there's that. So there's some positive, but there's also the negative. So the positive is good. Let's identify those and continue to use them even after the pandemic. But then on the negative side, one of the main worries I have is that coming out of the pandemic, even, this idea of, EDI, which is for, just to explain, that's equity, diversity, and inclusion, mm-hmm. Will become an optional extra, as in, we have so many important things to worry about first, mm-hmm. right? Health, economy. So this stuff, it just slides off the table. Mm-hmm. So there won't be resources or attention placed on this. I hope that's not going to happen, but in previous situations, that's been the case. So we can't think of this as an optional extra. It has to be embedded into how we recover from this year, mm-hmm. where this has to be part of every conversation and planning process, whether we're planning around public health, whether we're planning around, scientific initiatives, how to bring back the economy, who is going to be involved in all of that? How do we ensure that we're not making things inadvertently worse mm-hmm. by ignoring it because we're like, we're too busy with, the main issues around, making sure everybody has a job, for example. But when we say everybody, how are we making sure that's really everybody? Those conversations, I hope, become embedded into the process of post-COVID recovery. Who knows? Mm-hmm.
Are you hopeful that they will, or?
I think a lot of good signs, at least in Canada. Yeah. So, we are, we interact a lot with NSERC, for example, which is the main funding agency for STEM in Canada. So, and they're very focused on making sure that, the EDI is front and center now in almost mm-hmm. all of their initiatives. So, I'm hopeful because the conversation is happening and they're aware that this is an issue. It's not an easy thing to fix because how do you address how different people are impacted by this and how to assess? For example, let's say next year we have to evaluate grants, which is something standard that is part of the research process. Mm-hmm. So how do you evaluate somebody's research output during COVID and post-COVID, and for how long? Is there going to be an impact? And how do you adjust appropriately? Those are not easy decisions, but we do have to, deal with them.
Absolutely. All right. So I think we're going to move into the last pre-planned conversation topic. So for anyone watching, now's the time to hit us in the chat with questions. I'm going to throw something on the screen and I want you to tell me what we're looking at.
Okay. Yeah. I think that it's probably pretty obvious to most people. When I asked you to guess, I know that you kind of were on the right track. You said, it's probably from India. It's true. So this is a building in India, and I wanted to show something from my childhood, actually growing up there, and my memory. And this building was very important in my memory because actually this was the first school I went to in India.
Okay.
After kindergarten, that is. So yeah, this is the Hyderabad Public School, and it looks really fancy, right? Not like most schools because it's a converted palace. It was a public school, and I was in the first group of girls to actually go to this school. So that was also kind of an important moment, I guess, for the school as well. And so when I grew up, I had all these great memories of this beautiful building. And I remember one of my favorite places was this incredible library. You walk in and these ceilings so high that you couldn't even almost see all the way to the top because the books were stacked, right? So you didn't even know what books were right on the top shelves. I never found out. But I remember it as such an amazing, mysterious place. And there were corners and nooks that nobody had discovered for years, maybe. Right? So I loved that building, great happy memories. And I thought that all schools looked like this for a long time. I was a kid, right? What do I know? Mm-hmm. And then we moved, and I had to go to another school, and I was very disappointed.
So I love that idea of like places where you go and there's like always a new nook to discover. I love that as a kid. I still get excited whenever I go into somewhere like that as an adult. You mentioned the library being like full of books. So how did you end up settling on the physics book? How did you kind of get your way to being interested in, physics, computer science, and mathematics?
I think for me, even before I realized that I love science, I did, because another very strong memory I have from when I was a kid was that, we didn't have a TV at home when I was growing up, but our neighbors had a TV. But we were only allowed to go over to the neighbors and watch TV on Sunday mornings. Why? Because on Sunday mornings was when Star Trek was on. like original Star Trek, which is kind of dated, and that was like the highlight of my week. And for my brother and I would both go there, and everybody else would be doing their own thing, and there'd be noise everywhere, people shouting, but we'd just be hooked, watching the TV and this program. And my imagination would fly, right? So I think that's probably when I first started loving the idea of science and exploration and all of that. And eventually I chose to study math because I was good at it. So I think this is a combination of something that I loved and something that I was good at. I'm like, I could combine those two and, do something in physics, because I can apply the math and pretend that I'm going to eventually go on a spaceship like Star Trek. So that's where it all started. And then I realized that this way I could also, share physics with, the next generation by being in academia, education and all of that appealed to me a lot too. So that's the path.
Mm-hmm. So I get, and from a practical side, for students who wanted to get interested in quantum science today, what would be the biggest piece of advice you would give to them?
I'd say that it's actually, they have good timing, because I remember back when I was starting, quantum science as it is today, which is, almost like a mainstream thing. Everybody knows quantum computing, right? Back when I started, it wasn't even a word almost. So it's, in that sense, it's good timing for students. As far as I know, everybody with a degree in this area who wants to be employed in industry or academia does have that opportunity right now. It might change in the future, but that's how hot the field is right now. So I would say steps for students would be to, of course, try to get a physics degree, but you don't have to only have a physics degree. As we know, the field is much broader now. As you mentioned, you're going to have some chemists on the show, and also, mathematics, as we know, mathematicians, computer scientists, chemists, physicists, of course. There's a whole range of ways you can enter the field. And you can also, I think even broader than that. So for example, if you're interested in I don't know, environmental sciences or finance, right? One of the things that's kind of missing now is to understand how do we take some of this quantum technology that potentially will be scalable in the future and identify the right way to map real world problems in a way that a quantum computer would be able to solve. So in order to do that, it's not enough just to know the quantum piece. You also need to know about what's the big challenging piece in finance. Is it a search question? Is it a random number generation question? Which part needs the quantum input? Not every part will need it. So only certain types of problems so far that we know of can benefit from some kind of a quantum approach. So how those problems are part of different fields like medicine or finance or health, climate change and so on, environmental science, is still a pretty big open area. And the final piece I'll mention is, even if you're not into science at all, and now, John, and you and I, we did this one panel recently, right, where we explored the societal impacts of this kind of technology. So if you happen to be interested in law and the impact of different technology on law and policy, that's a growing field and very important to be exploring right now when this particular sector is growing. So that's another example. Or not just law, there's ethics, there's all kinds of international, like things like international relations even, right? Are we going to work together or not? So
Absolutely.
It's kind of amazing how many different ways you can enter this field and ask. Well, as I said, it's about asking a question and trying to apply a way to answer that question.
As the field grows, that umbrella just starts encompassing more and more and more and more and more.
Yeah, exactly.
All right, so we've got a couple questions in the chat. I'll let you pick. Do you want to start with science or with social?
Either one. Let's go with science.
Let's go with science. Okay, so the first question we have is, I believe, from Syed. He's wondering, in theory, are things like these long-term weather forecasts, is there a direct link between studying quantum chaos and long-term weather forecasts?
Actually, no. So here's an answer that is actually definitively known, that quantum chaos is not going to help us predict weather better. And this is why I say that, because on one hand, weather forecasting, the reason it's not very good, or at least a reason I should say, is that because of chaos theory, we already know that even if, for example, you try to run your prediction model for just on your standard computer using very, very well-known equations, perfectly well-known parameters, and you run the model, you're not going to have good predictive power beyond a week or so. Why? Because it all depends on where you start. So if you have to put in the temperature and the pressure and the wind speed and whatever else, right, that you use to run your model, unless you know those to literally infinite precision, you're never going to get the same answer when you run the model. That's what chaos means. Remember I said the butterfly flapping its wings? Well, by saying there's a butterfly somewhere there, that means that wind speed you put in may be not quite right. And the minute you change it, you're going to eventually have completely different predictive predictions compared to what the real system will eventually do if you had actually included the butterfly flapping. So that's why we already know that we're not going to be predicting weather. So unfortunately, quantum chaos will not help. But I like the question because it's something I can answer very precisely. Very rare in quantum chaos. So thank you.
That helps. So we have another question from Shivam. We spoke a lot about research, about research into EDI issues. And when we talk about EDI, there's kind of a standard thing where we almost always get caught in the trap of only talking about women in science. Shivam's in particular wondering if there's been any research or any data collection with respect to persons with cognitive or learning disabilities in physics. So
the answer is not a lot. However, there is an upcoming study which will be published pretty soon, which is a survey of the Canadian physics community and the demographics. Mm-hmm. And so part of that survey asked questions around the issues of a whole range of questions around identity and disability and experience and so on. So there might be some information there. More broadly, there are some studies, not based in Canada so much, but in the US, but the Canadian physics demographics is fairly similar, of course, scaled down by a factor of 10, but fairly similar to the US. So there is some data from the US. But broadly speaking, there's a big challenge because, of course, with disability, it's not always a visible thing, for one thing. So it's hard to identify. And secondly, there's issues around, being comfortable, disclosing disabilities and talking about those issues. So that, in fact, has been a huge problem with, both collecting data, understanding the experiences of people with disabilities, and also doing it in a way that actually preserves that kind of privacy and confidentiality, right? So Canada has very strong such privacy rules. So for example, if you have any data you collect, but there's less than 5 people in your data set for that particular group, then you can't disclose anything about that group because of privacy and confidence. So and we're talking about numbers that could often be that small. So it's a very, very hard problem, unfortunately. But we're working on it.
So that's an active survey by the Canadian Association of being run by the Canadian Association of Physicists. Do you know if that data is going to be made public when it's compiled?
Yes, of course. So fairly soon, within the next month or so, there will be an initial summary available. And then going forward, there'll be a much more detailed analysis presented. We're working on that. The Canadian Association of Physicists is working jointly with my research team at the Center for Women in Science. So there's a lot of great data. So I'm very excited about being able to help with, bringing that to a much broader community very soon.
So on a slightly different line, so Mayar is asking if you've ever experienced research burnout. You keep a very, very busy schedule. Have you ever just burnt the candle at both ends, let's say?
Often, right? These days I feel like all the time. But I don't know if that's, COVID related, burnout or research burnout. It's very hard to keep it straight these days. So there's generally, a sense of stress right now, I think, for many people. But yes, of course, there's burnout that happens. That being said, though, I will also say that we've spent a lot of time talking about things like work-life balance. Is a very common phrase that we hear often around women who are working in the field. I don't think that a group of men usually get together to talk about, maybe I'm wrong, you can tell me, John, but talking about work-life balance among men has not been traditionally common, I think.
Definitely not common, I would say.
Okay. So, but with women, it is actually common. And I feel like that's, again, obviously that's clearly gendered. I don't understand why one group would need that more than the other. The reason it's been done that way is because there's this assumption of caregiving that's assumed to be on women, and therefore they need help with it. But to come back to the question of burnout, there's certainly strategies to be able to manage time and stress. And if that's something that anybody's going through, I certainly hope that they reach out to those who can provide, for example, mental health support. If you're a student, there's lots of available support for that. So I think that that's an important thing to keep in mind. And secondly, I feel like sometimes just finding the balance itself is very stressful. So personally, I'm like, I forget the balance. There are days absolutely when I don't want to do a thing because I can't. My brain is not focused, and I allow my brain to tell me that it's not willing to work. But so I feel like for me, it's more of an organic process of allowing extreme work and then allowing extreme rest as well. Because if we all try to reach some artificially set bar of, yes, this is the ideal balance, and then you will be stress-free and happy. Of course, we know that's a myth. So I feel we all have to figure out ways that work for us personally. And for me, it's all over the place, right? Some days or some weeks are just intense focus and work until I sort of really have to just step back. And then, I trust my gut to tell me, okay, this is enough, and then I step back. And if I don't trust myself, then I do reach out for help and say, this is what I'm feeling. What do I do? And how do I cope? So I think we all need help. We're not experts on everything.
Absolutely. Let's see. So I think I almost feel bad because that seems like a good place to end it, but we do have a couple science questions I just want to squeeze in here at the end. One is from Debanuj. Can quantum computation simulate the dynamics of large networks? Is that a thing?
So quantum simulation in general is a big area of research. However, we're talking about simulations on very small real-world computers right now. So large networks of anything is not possible right now. Going forward, would it, if the quantum computer could be scaled up, so we're talking about thousands or tens of thousands of qubits, then absolutely, we could think about, mapping some kind of a network to the quantum computer. In fact, even things like a molecule is kind of like a network, right, of connected, particles. So that's something that people are certainly thinking of in the quantum simulation kind of approach. So yeah, sure, in the future. Right now, I don't think that it's, we have large enough scalable quantum computers to really think about large-scale simulations of complex networks.
Mm-hmm. And then our last question is from Miazia. First off, she says, thank you for the chat. And second off, she's interested in hearing what some of the greatest challenges you and your peers are facing in quantum security and information. Obviously, that's a very, very broad question, but I guess in your particular stream, like what would be kind of either the biggest challenge or like the biggest holy grail?
So it's almost too big of a question to answer. Quantum security. I think the basic sorts of building blocks have been identified. One of them, of course, is quantum key distribution, which is kind of an amazingly simple and but yet powerful scheme to build encryption protocols with. But going forward, the question is, how do you build it into current available systems, right? Because yes, it's nice and theoretically a lot more is possible, right? So there are all kinds of protocols to do these kinds of network quantum computing. My own group, because we're theories, we're theorists, so we love to play with, what could we do if we had a large quantum network? So we discuss controlled teleportation and secret information and privacy, and so there are many protocols, including things like blind quantum computing, network quantum computing, and things like this. But how do you implement that? It turns out to be one of the biggest problems. And how do you implement it in a way that's secure? So the next steps, I think, in the real world for those who are actually developing these bigger quantum networks that have things like quantum, the ability to do QKD, quantum key distribution, the big challenge there is errors. And it's actually the same challenge as in quantum computers. Quantum computers also have errors. In the communication security sort of framework, the errors actually allow hacking hacking of the system. Mm-hmm. So because of that, having the error rate low when you transmit information security is very important. I know recently China has made huge progress on that, and they claim that they are now being able to generate keys using quantum key distribution and their satellite-based system to be able to generate low enough error rates that they can ensure that the key is secure. So that's a big step. And then the next step is, how do you then add that layer of quantum key distribution to the existing kinds of whatever fiber optics and Wi-Fi systems we have today? It's not, of course, an easy thing. You want to be able to do it without having to replace the entire system.
Yeah.
It would be good if you could piggyback a little bit. So we talk about wrapping a layer of quantum security around whatever exists. So how to do that in a practical as well as, resource efficient way in terms of time and money and whatever other resources you need technology-wise, that's a huge challenge.
Mm-hmm. Like we said at the start, pick a challenge that's going to take you 40 years to solve it. So there's still a lot of work left to be done.
Progress, I can tell you, even during my own 10 or 15 years in this field, I could not have predicted that today we'd be sitting here and talking about existing quantum computers and satellites doing QKD. I don't think I would have predicted that. I don't know about you. What do you think?
Not a chance. Not a chance. Right? It's moved fast.
No. So that's, I guess, there's challenges, no doubt, but I think we're moving much faster than many people had expected. So that's good.
Yeah. That's encouraging. Well, yeah. Shohini, thank you so much for joining us today. This was a lot of fun.
Yeah. I love chatting with you, John. So thanks for having me. Although, where's the fireplace, virtual wood? We have to get on that project.
I know. Okay, we're going to take that one offline. There might be some IP issues if we discuss that one publicly.
Quantum security.
Exactly. Very key. All right. Everyone, thank you for joining us today. Next month, we'll be back with Thomas McConkey, IQC alumni and current microwave design engineer at IBM Quantum. We've also put a link to a survey in the chat. If you take a moment to fill that out, that's going to help us understand our audience better and shape the next virtual events coming out of IQC. Also, keep an eye on our social media and this YouTube channel for more information about the Quantum Shorts Film Festival. We'll be having that screening on February 13th. Until then, have a wonderful night, and we'll see you next time.